Hi, I'm Daniele from Nuremberg, Germany. I will be giving a talk about modules and the free secret spices. Speaking of spices, last year I learned how to use more of them and more creatively in preparing my dishes.
Hi, my name is Erica. I'm from Seattle. My session is titled An Introduction to CMake Presets.json, and one new skill I picked up last year is gardening.
Hey there, my name is Cy Brand. I'm Microsoft C++ developer advocate, and I'm the host for this conference. One thing I have learned during COVID is live coding and streaming it. I've been doing C++ 20 ranges from scratch on Twitch every Wednesday, so maybe see you there sometime.
Hi, my name is Sunny Chatterjee. I'm an engineering manager in the C++ team at Microsoft. In this year's Pure Virtual Conference, I'm going to show you how you can use code analysis to write safe C++. I live in the Seattle area, and this year during COVID times, I picked up a new hobby, which is gardening.
Hey everyone, welcome to Pure Virtual C++ 2021. I'm your host. Okay, I'm seeing a lot of things change, but welcome to Pure Virtual C++ 2021. I'm your host for today, Cy Brand. Our second year.
Hi, I'm Daniele.
Hi everyone, welcome to Pure Virtual C++ 2021. I'm your host, Cy Brand. This is our second year running this conference. Last year I ran everything from my laptop. This year I'm not running everything from my laptop, but hopefully everything from now on will be smooth sailing. So we are streaming to a bunch of places now. We are streaming to YouTube. If you are not on Microsoft Learn TV, then please go over there if you would like to ask any questions to our speakers. That's where all of the live chat is going to be happening. Also, please do have a look at the code of conduct underneath the chat window if you'd like to ask any questions. That's just to make sure that, okay, now I am live. Okay, hi everyone. My name is Cy Brand. Welcome to Pure Virtual C++ 2021. This is our second year running the conference, and last year I ran everything from my laptop, which had some difficulties. This year, hopefully everything from now will be very smooth sailing. So we are streaming to a few places today. If you're watching from YouTube, I would recommend heading over to Microsoft Learn TV, which is where we're going to be hosting our Q&A. So if you'd like to ask any questions, please go to aka.ms/learntv. If you would like to ask any questions, please do read the code of conduct, which is right underneath the chat window. It's just to make sure that everyone has a safe and fun time. Today we have 3 hours of content made up of 5 sessions. You can go onto the website to make sure to check out the schedule. And we've got content on modules, on CMake, on code analysis, a whole bunch of stuff. We also, in the last week, published a bunch of pre-conference videos to our Visual Studio YouTube channel, which you can find and watch. They will all be available after the conference as well, including all these sessions today. You'll be able to watch them on Learn TV and on YouTube. So if you miss anything today, don't worry about it. You'll be able to check it out later. With that, I'm going to move on to our first session today, which is our guest speaker, Daniela Engert. She is one of the foremost experts in C++ modules right now, and also one of the best educators, I think. So I'm super glad to have her on today to tell us about modules and the 3 secret spices. So please welcome Daniela Engert.
Hello everybody and welcome to my talk on the 3 secret spices of C++ modules. I'm Daniela, an electrical engineer living in Germany. I'm creating software professionally since the late 70s. I will give you a very brief overview of what modules are about and how they look like before I move on to the 3 key features that shape the functionality of modules: divisibility of names, the notion of reachability, and then linkage, or then when does the same name refer to the same thing. Modules are one of the major additions to C++20. They are probably the most transformative feature in the sense how we think about designing interfaces and composing software, and how they possibly help us to avoid hard-to-detect problems. Folks, I think we are just doing it wrong now. We follow the book of John Lako's book about layering software and designing large systems. We protect the library implementation from being invaded from the outside, but our poor library interface in the interface headers has not this kind of protection. Our software may tamper with the text of our library interfaces, or they may even be outright hostile to different kinds of other software without even knowing. This is not good. For technical reasons, the interface header might even need to contain implementation details of the library that are required to form the interface, but are actually not meant to be used outside of the library, like, for example, template definitions or inline functions. In some cases, even all of the library implementation is included in the interface. The interface header is then textually inserted into the translation unit of the library implementation and also into the client translation unit that consumes the library. In the C++ compilation model, boundaries exist only between translation units. Foreign code is barred only from intruding the use of the library implementation. The interface headers just do not benefit from this level of protection. The compilation of a TU starts out from a given compiler state as set up from the compile environment, like compiler flags, macro definitions, and it starts with an empty set of declarations. At the point that the library interface header is started to being processed by the compiler state may have changed by all of the stuff the compiler has already processed so far. The compiler state at that point may be different in different translation units, giving rise to different interpretation and meaning of the literally identical C++ text in the interface header. This may lead to subtle bugs because of ODR violations, because definitions might no longer be the same in all parts of the program. Again, we are doing it wrong. At the end of the compilation process, an object file is generated and all of the compiler state with all of the collected information is simply discarded. Using the library again in a different translation unit requires compiling the same header files over and over again. That's inefficient. Quite some time ago, at about the turn of the century, it became apparent that they need to do better. So fast forward to today, we finally can do better now. Modules change the compilation model in a way that the interface of a library is no longer textually inserted into a TU, but rather becomes a TU on its own. This shifts the protection boundary to the place between the library and the client code, right to where it belongs to be. Well, that's just a minor drawback though. we need a new communications channel that makes the contents of the interface visible to both the implementation of the library itself and also to the clients of the library. This channel is a compiled form of the interface with an equivalent representation of its contents. The compiler environment is no longer a concern. The semantical meaning of the interface is immutable. It's compiled only once, and there's therefore no place left for ODR regarding the contents of the interface. The additional artifact is called build or binary module interface, or in short, BMI. Everything in the BMI is available within the library, but only selected parts become available to the outside. We architects of the library interface decide on which entities we want to make available rather than being forced by technicalities of the language. So we can do better. The compilation of the interface starts from a known compiler state that is still untampered by unrelated C++ text. Besides the object file, the compiler will also emit the BMI with the representation of the language entities that it's collected during the compilation process. Implementations may also put some additional info about the initial compilation state into the BMI to prevent ABI problems. So compilers can do better as well, and tools too. This is the way. So how does a module look like? In the new modules world, there are not only modules, but all the already existing code that's outside of the module and need to be used again. For the sake of consistency, we call this part of the world to be the so-called global module that has no name, and the code in there follows all the traditional rules of the language as they know them. Beginning with the declaration of a module and giving it a name, we enter the module purview. The module name must be unique to each module within a program. Every entity that's declared in the purview becomes part of a new domain of names that is separate from all names in the global module and from all other modules. Be aware that this new name domain is not a namespace. Names introduced within the purview can be referred to from the inside of that module, but not from the outside. Then the module declaration has the export specifier at the beginning. It's the so-called module interface translation unit. Each module has exactly one. By prepending a declaration with an export keyword, the declaration is made available to the outside of the module. Other translation units that import this module can then refer to the exported name. Without the export keyword in the module declaration, it's a module implementation unit, which you can have as many of them as you as a library developer want to. Optionally, a module translation unit might start with a piece of code that is not part of the module purview, but rather the old-style global module. You can put your existing code or other code living in the global module here into the so-called global module fragment. This code can then be used as usual from within the module purview. Modules may also import other modules, either as a non-exported implementation detail, or they may even become an integral part of the module interface by re-exporting their interface. You cannot see the provenance of the entities that a module exports. The composition of a module interface is totally hidden. There's actually a variety of module translation unit types besides the primary module interface and the module implementation units. Each of them has a unique set of properties and features. You can pick appropriate types to compose a module. Header module units are special. They have no name, no architected interface, and even maintained other translation units by leaking preprocessor macros into them. So how do modules achieve their stated goals? The first part of the answer is related to names and their visibility. Visibility is probably quite well known to us so far. The C++ standard says that a name is visible when it's not hidden. That's only partially helpful. So basically, a name is visible when it can be found during name lookup. But before that, a name needs to be introduced by a declaration in the first place. And this must happen in this same translation unit. Compilers never look into other translation units. This seems obvious and totally familiar to us because these are the C++ rules, but other languages may have different rules. So the visibility of a named entity depends upon if that name is declared within the translation unit before it's being referred to, and if the programmer uses an appropriate lookup algorithm that is capable of finding a name in the scope of its declaration from the scope that a name is being looked up from. Otherwise, a name is invisible at the point of lookup, but it may still be visible from a different point of lookup. If we perform name lookup for entities at class scope, the rules are a little bit less restricted in case of types of dependent types in templates, or if the names are referred to while still being in the definition of a class body. In these cases, names can be referred to even before they are defined. The lookup of these yet unintroduced names is deferred until after the names are actually introduced. Sometimes it takes different kinds of lookup algorithms to find a name. Maybe a name in a sibling namespace or in a namespace, in the outer namespace, that a name of an entity of the same name is also declared at a namespace that is nearer to the point of lookup. Or in the case that you need an RDL, argument-dependent lookup to find an entity which are so-called hidden friends. These hidden friends are friend functions that are declared at class, in the class body, but are not part of the class, but rather than are technically living in the namespace that surrounds the class. And it can be even weirder than that. We can define classes within a function body that returns instances of these classes by return type deductions without even mentioning the name in the declaration of the function. The returned object can be used as usual, even though the name of the return type is totally invisible outside of the function. The compiler still has full knowledge of the type of invisible name though, because it can reach into its definition. It has compiled the definition in the function body and returned this information. So, an entity being invisible does not imply it to be unknown. So far, TUs erect barriers between them that make names declared in different translation units totally invisible. Modules extend visibility across translation unit boundaries by passing names declared in the module interface translation unit through the BMI into other translation units that imported BMI, similar to wormholes in the universe. Remember, visibility is only about names of entities to make them available for name lookup. If a module translation unit imports a BMI that's compiled from another translation unit of the same module, all names declared in that other translation units become visible. By importing the BMI, these names are introduced into the translation unit as if they were introduced by compiling the declarations themselves. Marking an entity in the primary module interface as exported, the names of only those exported entities can be introduced into TUs outside of the module. All other non-exported names in the BMI remain invisible.
So exported names become visible everywhere. Non-exported names become visible only within the module itself. So it's you, the library developer, who decides which names in the interface become visible and which names remain totally hidden outside of the module. So far, we've hardly made a distinction between the visibility of a named entity and the knowledge of other properties of that entity. We have seen one example where was a disconnect between visibility and the ability of the compiler to reach into the definition. This notion of reachability of declarations and properties is separate from and orthogonal to the notion of visibility. This distinction hardly ever bothered us so far. In the traditional world, the compiler knows everything about every declaration in the translation unit as soon as it has compiled it. And this is the case in every translation unit in the traditional world. But now, reachability becomes important in the modules world. BMIs compiled from module interfaces do not only act as a tunnel to transport names to make them visible, their second duty is to make declarations in the module become reachable when necessary. In this example here, the module mod imports another module stuff as implementation detail to use an exported class as member variable in class S. This class is not exported from module mod, but returned from the exported function foo. Class S has a member function what that returns the result of calling member function message on its member variable, without ever mentioning the name of that return type. So far, importing another module forms a dependency on that other module. Its BMI must be available for compilation. But there are more dependencies. The non-exported class S uses a non-exported type from another module as member variable. Struct S has a member function that uses this member variable in its definition. Functions return types that are either explicitly named or implicitly inferred without mentioning their names. At least some knowledge about these entities must be available at compile time to give meaning to the code. Then the translation unit on the bottom imports the interface of module mod. Only the name of the exported function foo is visible. Nevertheless, the compiler knows enough about the properties of the object that's returned from foo. It has a member function what, and the result type of that member function has certain properties that can be checked for at compile time and can be used at runtime. Let's look at the module stuff that was imported into our module mod. The module exports two classes that derive from non-exported base classes. These base classes are defined within the module, and one of them uses type string from the standard library as a return type of member function message. Remember, this member function was used in the member function what of class S defined in the previous module. So through inheritance and return types, even more dependencies are formed that ultimately extend into the standard library. All declarations encountered along this dependency chain that are originating from exported entities of a module interface need to be available from the outside of the module, even when the name of these declarations still remain invisible. All these declarations and their properties are said to be necessarily reachable, and therefore must be part of the BMI. Other declarations outside of the dependency chain are not necessary, but may still optionally be part of the BMI and be reachable, or they may be not. Preventing these declarations from being part of the BMI is not mandated by the standard, but is implementation defined. In this example, all declarations in module stuff are necessarily reachable from its own interface, but only some of them are necessarily reachable from the interface of module mod that imports module stuff. So what are the semantic properties of declarations or definitions? Some are mandatory, some are optional, some are defaulted. Let's define a simple function that takes an int and returns an int and give that function type a name. Implicitly and by default, it has also an exception specifier, and it's living and having external C++ language linkage. We can declare a function bar of this function type and put it into a namespace and give it a different language linkage. We can give additional semantic properties to this function declaration, for example, a function name, function parameter name. It's still implicitly external. It may have an inline specifier and an attribute, and if it's a definition of this function, it also has a function body which introduces additional declarations. The function parameter might have a default parameter, a default argument, and this default argument must be of a complete type, so the class type must even have a fully defined function class body with additional declarations, properties, and names in them. Everything shown here is must be necessarily available and reachable to make use of this function bar. In the compilation model of C++, each translation unit is compiled separately and independently. The linker then puts all the pieces together and forms a final program. The ability to do so meaningfully is called linkage. It describes properties of the API like calling conventions, and it prescribes consistently applied rules of forming linker symbols from entity names. All that such that entities of the same name in different translation units result in the same linker symbols, and also in compatible calling ceremonies. The linker will then select one of possibly multiple definitions if declared legal by inline, or complain if there's more than one of them or none at all. The formation of linker symbols is augmented in the world of modules to allow for additional semantics of names declared within module purviews. In this example here, we see two different modules declaring two different non-exported functions foo that are invoked from the bodies of exported function definitions bar and bus in namespace A. The language rules demand that importing both modules into the same client translation unit causes no problems whatsoever, even though both modules declare functions of identical names in the same namespace. As members of the respective module purviews, these functions are said to be attached to their modules. Namespaces extend across translation unit boundaries, and they are therefore not attached to modules, but rather attached to the global module. In a sense, names attached to a module seem to carry kind of a scent or branding that isn't noticeable at the language level. Cat owners know what I mean. This scent is necessary to make them distinguishable when forming the program. Names attached to the global module without name don't have that scent. To do so, we say that non-exported entities have module linkage rather than external linkage. Besides that, they both are just the same. Exported entities still retain external linkage despite being attached to the module. Then the compiler forms linker symbols from entities attached to a module with either module linkage or external linkage. The scent that marks these entities as belonging to that module becomes apparent in the mangled linker symbols. Here we see names manglings by different compilers. Symbols formed from name with module linkage must be different from symbols of entities with identical names in other modules or the global modules. Therefore, they contain parts of the in their symbol that are formed from the module name. This is another instance where the module name is actually has actually kind of a meaning. Symbols formed from exported names may be distinguishable, but they don't have to be. So the module name may be part of the mangled symbol name, or they may not. We call this difference in linker symbol formation to be following two schools of thought in regards to module ownership. There is the so-called strong ownership model, which retains the provenance of a symbol, and the so-called weak ownership model, there the provenance is removed. Neither is better or worse by itself, it depends on the use case. For example, in the strong ownership model, identical names can be exported from multiple modules and used in separate translation units without causing linker errors. Whereas in the weak ownership model, exported names can be moved freely between modules or from headers into modules. In certain situations, the loss of provenance may cause unpleasant surprises though. Here in this particular example, an unfortunate customer buys libraries from two different OEMs. Both libraries are delivered as binary static libs with interface headers. This is typical in some industries, for example the one that I'm working in. Both of them happen to use the same library from a third party, but in different but compatible versions. The use of a third-party library is an implementation detail that is in no way exposed to us clients and is totally undetectable at the language level. This third-party library happens to be made available to both OEMs through a module with different module names, dependent on the library version. All libraries work perfectly, but the poor customer, that's possibly me, that buys these OEM libs and uses both of them in the same product might end up either as a happy camper or face the unsurmountable problem of not being able to link the problem, depending on the compilation platform. And the origin of the problem lies in the third-party module that the customer isn't even aware of, and that both OEMs refuse to accept as a defect of their library. In cases you are concerned about this divergence of behavior on different platforms, never mind. We've got ways to make this fail also on platforms that follow the strong ownership model. By explicitly giving a name either C or C++ language linkage, the name is reattached to the global module and supposedly mangles accordingly. At least MSVC does. If you need to simulate a weak ownership model with a compiler that follows the strong ownership model, you can explicitly give exported names C++ language linkage to detach them from the module. This may also come handy if you need to forward declare a name living in the global module from within the module purview. But please use this feature only if there's no better option like including a header in the global module fragment. So, to give a recap, using an interface in compiled form rather than by textual inclusion, this isolates its meaning from the compiler state at the point of use, it doesn't taint translation units unwittingly, and it reduces the chance of ODR violations. Exporting names selectively makes visibility an architectural decision rather than being technically unavoidable. The representation of declarations in a BMI and making them reachable guarantees identical interface semantics everywhere. And lastly, augmenting linker symbols with their provenance makes TUs less promiscuous. Here are some additional resources you might be interested in and also my contact details. And with that, Thank you very much for your attention.
All right, thank you so much for that, Daniela. That was a really great talk. I sure learned a lot about modules that I'll be able to use in my projects. So I hope you did too. Moving swiftly on to get us back on time, our next session is going to be on CMake presets.json. If you have any questions about the previous session, Daniela will still be in chat to answer them, so keep those coming. We're going to move on now to Erica and Kyle, who are going to tell us about this new feature of CMake. How are you both doing?
Good.
Good, thanks.
All right, I'll handle it straight over to you. Thank you so much.
Sounds good. Hi, everyone. My name is Erica. I work at Microsoft on the C++ team, where I focus on tooling for C++ cross-platform developers. And I'm joined today by Kyle Edwards.
Hi,
Now, if you
my
wanna
name is
introduce
Kyle. I work at Kitware. I am one of the co-maintainers of the CMake build system. I have contributed dozens of features to CMake, including the one that we're going to be discussing today, CMake presets.json.
All right. So what is CMake presets?
So this is a file that you put in the root of your project that specifies a set of common settings that you might want to apply when you're running CMake configure and build and test. So it'll let you specify things like cache variables and the generator and any other build flags that you might want. We started off with configure presets, which just set cache variables in the generator and whatnot. And then we also added build presets, which let you select which targets to build, and as well as test presets, which let you select which tests to run and which configuration.
And how did we end up with CMake presets?
So this started off, the Minecraft team at Mojang asked us to create a system for doing this kind of common setting things from the CMake GUI. So we started off by attempting to replicate CMake settings.json from Visual Studio and from VS Code. But we ran into some issues with it. There were a lot of settings in that were specific to Visual Studio, and there were some things that we thought about the overall structure of the file that could be improved. So we decided to, go ahead.
And at the same time, our team at Microsoft was aware of some of these limitations of CMake settings, and we were looking to address them as well. So when we learned about Kitware's efforts, we were able to share our goals and ended up collaborating together to come up with this new file format.
Yep.
So why should you use CMake presets, and how is it different from other CMake configuration files? So CMake actually supports two files that both live at the root of your repository. There's CMake presets.json, which is intended to save project-wide settings and be checked into source control. And there's also CMake user presets.json, which is intended to save user-specific settings and be excluded from source control. This ensures that project-wide settings can always be checked in and shared between team members, which makes it easier for new team members to get up and running, and also makes it easier to synchronize changes to your CMake and build invocations across the entire team. Like CMake itself, CMake presets is cross-platform, so you can use the same CMake presets file to invoke CMake on Windows, Linux, and Mac. And CMake presets can also help streamline build instructions for open source CMake projects, because you can pull down any CMake project that has a CMake presets at the root of the repository and configure it, build it, and test it locally using the instructions encoded in a preset file. And to help illustrate this a bit more, we're going to dive into an example, starting with configure presets that were added to CMake in CMake 3.19.
Yes. So the configure presets let you specify things like the generator that gets used. For example, the Ninja generator or Ninja multi-config or any of the various Visual Studio generators. And it lets you specify things like the architecture and cache variables. So we'll go through this line by line. So these first two lines, name and description. Name is just an identifier. Description is just a user-friendly description of what the thing is. And then we have generator, which in this case, it'll generate a solution file for Visual Studio 2019. But you can also generate Ninja files and Make files and Xcode projects. Inheritance, this is a little feature of the presets where if you have several presets that share a lot of common settings and you just want to change one or two things between them, then you can have them both inherit from a common preset that will contain all of those common settings. This is the architecture. So for Visual Studio, this sets whether you're building for x86 or 64-bit or ARM or anything else. And then we have cache variables. In this case, we're just setting the C and C++ compiler, but anything else that you would set with the -d flag on the CMake command line can be set in this cache variables entry.
Yep, and all of the command line options that you can pass to CMake from the command line map directly to an option in the configure preset object. And there's also build and test presets, which were added in CMake 3.20. Kyle, do you want to run through build and test?
Yeah, sure.
Cool.
This will, for the builds presets, you can specify a configuration. So for if you have a multi-config generator like Ninja Multi-Config or Visual Studio, then you can set it to the debug or release configuration. You can also specify a list of targets that you want to build and a parallel level and any other options that are available with --build. And for the test presets, you can also specify the configuration and a regex of which tests you want to run, and any other settings that are available on the ctest command line you can put in a test preset as well.
All right. So far we've been discussing how you can invoke CMake using CMake presets directly, so from the command line or maybe in a CI pipeline. But on our end, we also added support for CMake presets in both Visual Studio and Visual Studio Code. And support for CMake presets in both of these products is available now in preview. So for Visual Studio, that's 16.10 preview 2. And for the CMake tools extension and VS Code, that's version 1.7 of the extension. Because the same file, CMake presets.json, is used to drive CMake configure, build, and test, that means you can hop between Visual Studio and VS Code and leverage the full feature set of both products without having to do any additional project configuration. Because CMake presets is supported by CMake itself, this also means that it's seamless to reproduce the builds created or driven by VS and VS Code from the command line or in a CI pipeline. So the configure and build command lines that are constructed by Visual Studio and VS Code are the same CMake command lines that will be generated by CMake itself. Finally, CMake presets does allow for some vendor-specific options that live in a vendor map. We do use this for things like IntelliSense options or the Visual Studio remote settings, but these settings don't impact the construction of the CMake command line at all. They are ignored by CMake and they are only evaluated by Visual Studio and Visual Studio Code and are used to drive IDE-specific integration settings. So with that, I'm going to hop into a quick demo where I run through how to use CMake presets from the command line in Visual Studio, in VS Code, and with the CMake GUI. So I'll start with the command line workflow. So here I have a terminal open. I'm working at the root of a CMake project. It's bullet 3. It's an open source physics library. And I have a CMake presets file at the root of that repository. In this demo, I'm only using CMake presets.json, but if I was using CMake user presets.json, then that would live in this directory as well. I am using CMake 3.20 because that's when support for build and test presets was added. This list presets command lists the union of configure, build, and test presets defined in CMake presets and CMake user presets. And to invoke configure with CMake presets, all I need to do is pass the -- preset option and then the name of the configure preset that I want to use. So in this case, I'm configuring the project with x86 Windows configure preset. And while this is running, I'm going to quickly open Visual Studio just to kind of walk through how I've set up this preset. So as Kyle mentioned, presets allow for inheritance. So I have a base configure preset, which is one configure preset in this array of configure presets that sets some common configure settings that I want to apply to all of my configure presets. And then I have this x86 Windows configure preset that inherits from base and sets in a few additional settings, like in this case, my target architecture, which maps to -A. Looks like this is still running. Sharing my screen with StreamYard does slow things down quite a bit for me, so bear with me as we work through these examples. But I can chat a bit more about this file. So I have x86 Windows configure preset. I also have a few configure presets that are specific to Linux. So they specify a GNU toolset and a couple other settings. I also have an array of build presets, which, as Kyle mentioned, are used to specify build settings or any command line arguments that you would pass to CMake after --build from the command line. So that's things like verbose build, clean build, any native build tool options, things like that. All right, looks like this is still running. I can also hop on over to the CMake GUI. So this is a application that is maintained by Kitware, and it's used to inspect and modify CMake cache variables. So, and sorry, I know this is a bit small. I'm just going to quickly run through this. So you tell CMake GUI where your source code is. So this is the same directory that I have open from the command line right now. And then you would select your preset, and I can't do that quite yet because configuration is still running here. And I can fail on this in a few seconds if it's still running, but it really slows down my machine. Here I have the same file open in VS Code. So you can use it from any environment. Is it possible that I take a few questions while this is still running? Oh, okay, because it's kind of necessary for the rest of the demo. All right, it's almost done. Okay. That is finished. So I'm going to hop on over to VS Code really quickly and just show you how you would use the same CMake presets file in VS Code. So this blue bar across the bottom of VS Code shows the status of my environment. So in this case, it's showing my active configure preset. So this x86 Windows configure preset, and you can change that by either clicking on that icon or running the CMake select configure preset command. Likewise, you can select your active build preset and test preset using the CMake select build preset and test preset commands. And those are also shown across the bottom of this blue bar in VS Code. So the same configure and build actions that I can take from the command line, I can take from inside VS Code as well. We don't have to sit through this, but to quickly show how you would build from the command line, you can run CMake --build --preset, and then the name of a build preset. So this basic example GUI build preset, in this preset, what I've done is I've used the targets option, which is equivalent to passing --targets or -t from the command line, and it can be used to specify a subset of targets in your entire project that you want CMake to build. So this is just building one target. And now we can go back to the CMake GUI because generation has finished. But basically what you can do is you can select your active configure preset. So for me, that's going to be x86 Windows. The active configure preset drives the build directory. And then when I click configure, that basically generates the CMake cache such that I can inspect all the CMake variables that are set in my cache and modify them. And so this includes a few CMake variables that I've set in my preset file. So in my case, that's like CMake install pretext, which is the install directory, and my C++ compiler, which is CL, things like that. All right, and the last thing that I want to show as a part of this demo is the CMake preset support in Visual Studio. So you can use all this in VS Code in conjunction with remote extensions on Windows, Linux, and Mac, because VS Code is cross-platform itself. But you can also use CMake presets in Visual Studio. So I could configure and build using the same x86 Windows configure preset that I was just showing from the command line. But in this case, I'm actually going to configure and build on WSL. So you'll notice that there are 3 dropdowns across the top of my screen here in the menu bar. The dropdown on the left is my active target system. And this is the system where CMake will be invoked to configure the project and build. So I could use my local machine. I can use a remote system that's connected over SSH, or I can use any WSL installation that Visual Studio picks up on. The dropdown in the middle indicates my active configure preset, and the dropdown on the right indicates my active build preset. And I've already configured and built this, so I can go ahead and start debugging one target. I'm going to use this app basic example. So this will, what is happening right now is that this target is launched on WSL using the front end of the Visual Studio debugger backed by GDB. So I'm debugging with GDB from Visual Studio, but I can leverage the same debugging feature set that you're used to when debugging on Windows. So I can step through my program. I can inspect variables on hover. I have my autos and locals windows, a nice visual call stack, things like that. The last thing that I wanted to call out is that in both Visual Studio and Visual Studio Code, we've added IntelliSense for configure presets, build presets, and test presets. So you'll get auto-complete suggestions based on the options that are supported by Kitware, by CMake itself, as well as any vendor, Microsoft vendor objects that are supported. And with that, I'm going to hop on over back to my deck. So that was a really quick run through of how these things are supported from the command line, from the CMake GUI, VS and VS Code, but there's a lot more there. So for more information, I would recommend checking out the CMake presets documentation, which is maintained by CMake and describes all of the options that are supported by configure, build, and test presets. And then for more integration, more information on the integration in both VS and VS Code, you can check out this announcement blog post, which links to our documentation, which contains more information on how to enable CMake presets integration. Again, both integrations are still in preview, but you can play around with them today, as well as more information on how to configure, build, and test your projects from a IDE or editor. And that's all I have. Kyle, feel free to jump in with more info, and otherwise, I think we're ready to take a few questions.
Yeah, I do see a good question here. Is JSON how you configure CMake these days didn't have its own domain-specific language? So the domain-specific language, the CMake list.txt, that has not changed. The purpose of CMake presets is oftentimes you'll see people write shell scripts and batch files whose only purpose is to invoke CMake with a G flag and a set of D flags and anything else that they might want from that. CMake presets is intended to replace those ad hoc shell scripts. So this is the JSON is just another thing that's on top of the CMake list.txt, on top of the domain-specific language.
Cool, thanks for that. Yeah, I've got some more questions in chat which I'll relay to you. So a few of them have been answered by folks already, but maybe you could speak a bit more about the relationship between CMake settings.json and CMake presets.
Right. So CMake presets is an orthogonal and recommended alternative to CMake settings. CMake settings is still supported, but there is full parity between CMake presets and CMake settings. So any command line that you're able to generate or drive with CMake settings, you should also be able to drive with CMake presets. There are a couple of benefits of CMake presets over CMake settings. So one is that CMake presets is supported directly by CMake, which means that it's seamless to reproduce your builds from inside Visual Studio from the command line or in a continuous integration pipeline. There's nothing that's kind of abstracted by Visual Studio. Another is that CMake presets is cross-platform, which means that you can use the same file to drive your configure, build, and test invocations on Windows, Linux, and Mac, and not just on Windows. And a third one is that CMake presets is supported by both Visual Studio and Visual Studio Code. So CMake settings was only supported in Visual Studio, but CMake presets is supported by both products, which means that you can hop between VS and VS Code without any additional configuration. So CMake presets right now, the integration is still in preview, so totally understand if you want to stick with CMake settings, but long-term looking forward, we're excited to support CMake presets because it is supported directly by CMake and should make your lives and our lives easier in the future.
And our hope is that other IDEs will take up CMake presets in the future as well. I know the JetBrains team was working on it. I'm hoping that eventually Qt Creator and Code Blocks and Eclipse, we want all those to integrate it as well.
Great. And there's another question on CMake settings, which is about you could only generate a build system which had exactly one configuration, i.e. one for release or one for debug, but not one build system with both release and debug configurations, even if you used a multi-configuration generator. So with CMake presets, can you describe multi-config generators properly so that Visual Studio? Yeah, go ahead.
So from the command line or in VS Code, you definitely can. CMake presets as a file does support multi-config generators. Multi-config support in Visual Studio isn't quite fully supported, and so Visual Studio generators are supported, which are kind of multi-config in nature. But for multi-config Ninja or other command line generators, in Visual Studio, we still do recommend that you specify configure or release builds in the configure preset, but that's something that we're aware of. And if you're working again in VS Code or from the command line, multi-config generators are supported already.
Great. Any other questions about CMake settings or anything else, drop them in chat. There's one other existing question on what is the effect of warnings dev level?
Kyle, do you want to take that one?
Yes, sure. So there's a distinction between user warnings and dev warnings. User warnings is for when the person who's invoking CMake does something that CMake says that maybe they shouldn't do or that might cause problems. Dev warnings are for when there's an issue with the CMake lists itself that is not the fault of the person who's invoking CMake, but whoever authored the script could potentially want to fix whatever issue is being warned about.
Cool, thank you for that.
Mm-hmm.
I think that's all of the questions in here. There's some other questions about Vcpkg support. Maybe we can touch on that for the video. Is this going to support Vcpkg other than just setting the CMake toolchain file?
So CMake presets doesn't really integrate with Vcpkg aside from specifying the CMake toolchain file. Vcpkg integrates with CMake as a whole and picks up on your specified target architecture. That's how they know what triplet to build automatically. And then separately, Vcpkg is supported in Visual Studio, but there isn't really other integration points between CMake presets as a file and Vcpkg as a tool, aside from where you would specify the Vcpkg toolchain file as a command line argument as a part of that cache variables object. But yeah, no integration, but there aren't really any integration points there. It would more be like the Visual Studio or the VS Code integration that would be more integration points.
Right, and if you do want more information about Vcpkg, then the very next session is going to be the one for you. Okay, so we're about clean on questions in chat. So does anyone have any others before we move on? Not seeing anything pop up. Okay, thank you so much, both Erica and Kyle, for joining and telling us about CMake presets. So I hope you enjoy the rest of your day.
Thank you.
Cool. So yeah, before we move on to our next segment on Vcpkg, if you've never tried out the CMake integration in Visual Studio or Visual Studio Code, that's something that we've been working a lot on in general, trying to make sure that MS Build has always been a first-class citizen in these kinds of in our IDEs, but CMake is as well now. We want you to be able to load up a CMake folder and just go on, build your code, test it, have it nicely integrated into the experience. So please do go away and try our CMake support in both Visual Studio and Visual Studio Code, and let us know if you have any feedback. We're always trying to work to make it a more pleasant and productive experience. So our next talk is on Vcpkg. So if you've never used Vcpkg before or heard of it, it is a dependency or package manager for C++. If you've used Conan, then it's something kind of similar to Conan. There's some differences in implementation, but it's a similar kind of idea, managing your dependencies without having to do it manually. And our speaker for this is Augustin, who is on my team in the Visual C++ team. Augustin, welcome.
Hey, Sai, how's it going?
Yeah, pretty good. It's absolutely horrible here where I am in Scotland. I have rain pattering on my window and it's cold and awful. I hope it's nicer in Seattle.
Yeah, it's been nicer lately, but we do get our usual 7 to 8 months of rain during the year. So
yeah, I always feel like, because I work with all of my team is in Redmond or Seattle and I'm in Scotland, although we're pretty much on different sides of the world, I feel like there's a connection there by just how much rain both Seattle and Scotland have. But yeah, thank you very much for joining us today, and I'll hand it over to you.
All right. Thank you, everyone, for joining us for Pure Virtual C++ once again this year. So what I will be talking to you about today is Vcpkg, which is the C and C++ library manager tool that we have been working on. And specifically, I want to discuss some of the latest features that have been developed over the past year and where we are with them. I've got a few announcements to make as well. So let's go ahead and get started. So if you're not familiar with Vcpkg, I will just do a quick intro. So Vcpkg, as I said, it's a library manager tool. Another word I guess you could use is package manager. And its purpose is essentially to make it really, really easy to acquire C and C++ libraries. Now, in the past couple of years, there has been an ISO C++ developer survey that's been going out. And one of the questions there is essentially, what are your top pain points of C++? And if you look at the answers, you will see there's a few ones that you probably expect, things like long build times, for example. But consistently in the past few years, since the survey has started asking that question, we've seen that managing libraries has been consistently the #1 issue in terms of, if you look at people who strongly agree with it being a problem, that was always at the top. And this is a problem that has been going on for a very long time. Vcpkg is designed to help solve that. So as it stands today, Vcpkg has over 1,600 public libraries. These are popular open source projects and also some of the smaller ones as well. I mean, it's a pretty large number, as you can see. You can install them for Windows, Mac OS, and Linux, assuming the libraries themselves actually support those platforms. The project itself is open source. You can find us on GitHub. We can feel free to fork it or add it as a Git submodule for your project or do whatever you want with it. Essentially, it's all out in the open. And we do get quite a lot of open source contributors as well. And we're very happy to receive their contributions and want to thank them for their ongoing support for the project. We really wouldn't have been able to grow as fast as we have without their support. And the way it kind of works is Vcpkg is very CMake centric in terms of things like authoring packages and getting things working behind the scenes. And it is written in C++ for C and C++ developers. And it is designed with both working in a local development environment and continuous integration in mind. So that's kind of a brief overview of Vcpkg. And one line I wanted to throw in here, our goal with Vcpkg is really for it to be the simplest solution for C and C++ dependency management. There are lots of different solutions out there. Some of them are solutions that individual organizations may develop. Some of them are actual package managers. Some of them are system package managers. But there's always some pros and cons to all the different options. With system package managers, for example, well, they're system specific, and you don't really have the same level of flexibility as you might have with a language package manager like Vcpkg or Conan. And with some of the in-house solutions that different people and organizations come up with, and you have to worry about maintaining them. They're not always open source, so it's they don't get as many contributions. And overall, it just continues to be kind of an ongoing maintenance problem to deal with. So with Vcpkg, it's a project that's out in the open. It's very active, and we're going in the direction of trying to really solve all the common problems that you run into when you're managing C and C++ dependencies. And specifically, if we're going to talk about what Vcpkg can do for you, first of all, Vcpkg builds libraries from source. This has been a defining characteristic for the product from the beginning. We often get asked, why don't we just provide pre-built binaries the way some other package managers like NuGet, for example, do? And the reason for that is that there are a lot of different ways you can actually build C and C++ libraries, and most of them will not work for your particular project. But that's actually not even the biggest problem. The biggest problem is when you're dealing with, let's say, a more complex dependency graph, and you have dependencies of dependencies, and some of those dependencies have shared dependencies upstream, and you have to deal with things like version conflicts. And how do you resolve that? Well, if library A depends on one version of Boost and library B depends on a different version of Boost, you have a problem, and that's something that you have to resolve. If you're not using a language package manager, you have to kind of resolve that yourself and figure out, okay, what version of Boost can I use? What version of these other libraries can I use? How do I install all the different libraries that I need in such a way that when I compile it all together and link them into my project, I don't have any problems. And this is the kind of headache that people run into, and one of the biggest reasons I think that people are saying dependency management is such a pain for C and C++. So Vcpkg kind of solves that for you. The way it works with our big public catalog is all of these libraries are actually compiled together as part of a continuous integration process. In fact, anytime somebody wants to update the catalog by maybe introducing a new library or updating an existing library, what we do is we actually force the whole thing to build at once and make sure that all the libraries work together. And what this means is that if I say I want some 5 libraries out of the 1600, I can expect them to just work with each other out of the box without me having to do any additional configuration, without me having to change the way they are compiled or changing versions or fiddling with them and trying to solve different problems that would otherwise be coming up. And the way we describe this is the whole catalog is like a version set of all these libraries. Now, there is a downside to that, which is that you're not actually you don't have the flexibility of being able to say, I want this version of a particular library and this other version of a particular library. You kind of have to live with whatever Vcpkg is currently providing, which is usually like the latest or closest to the latest acceptable version that compiles with everything else. But I will talk about more about that versioning problem shortly. But other things that you can do, so when you acquire dependencies, oftentimes dependencies have dependencies of their own, and sometimes those dependencies have their own dependencies, and you think you're going to install 3 dependencies and you end up installing 9 dependencies. And that's not, if you're doing this manually and building everything one at a time and going to individual GitHub repos to figure out the build instructions for each thing, seeing if it works for your build system, seeing if it works for your OS, that's not fun. Well, Vcpkg solves all of that for you. You can just tell it, okay, I want these 3 libraries, and then it will also install their own dependencies upstream so that although you just have to say you want those libraries, all of those like upstream ones also get set up for you, so it'll just work. And again, I talked about the version set thing, so the version conflicts, that whole thing is, that whole problem is avoided, which is really nice. And we have, in particular, some really good integration with MS Build and CMake build systems. Although you can use it with other build systems as well, but we do have some additional features that work for MS Build and CMake, and I'll be talking a little bit about that as well. And again, easy to use. This is the key. We want to make it extremely easy. When you go into, when you install a set of libraries, it's essentially as easy as going into the terminal and saying vcpkg install, and then you list a bunch of libraries. Maybe you might also specify how you want those libraries to be compiled if you want it to be something other than the default. So you might say, well, I want x64 Windows of this library, or here's a custom build configuration for something special that I made. You can create your own as well. So that's kind of how it all works. And this is kind of like the basics of using Vcpkg. But we have been investing a lot into improving the tool. We've added a lot to it since we got started with the project back in 2016. Of course, the size of the catalog was the biggest, most obvious change over the years. But more recently, we kind of took a step back and thought, okay, we've been really increasing the size of that catalog. And at this point, we've covered many of the major libraries that people want. But are there features in the tool itself that we can add to make this to make the experience even better? And yes, the answer is absolutely we can, and I'm going to go through them right now. The first of these is something called binary caching. Binary caching solves one of the problems that may come up with the fact that your Vcpkg builds libraries from source. So building libraries from source is good because it gives you the flexibility of building libraries in a way that actually work for you. So you're not downloading some random pre-built library that may or may not work depending on your particular build graph or whatever build configurations you require, whatever compiler flags and other stuff. So we want to be able to build from source at least once to be able to get that dependency graph set up nicely. And then once you have that, then you're good. Well, binary caching essentially allows you to do that exactly once and only once, unless you're making changes to the build requirements in the future. And essentially allows you to just cache those dependencies somewhere, or the binaries of those dependencies somewhere, and then be able to restore them as you need them. So the very first time you install a library of Vcpkg, by default, right now in the tool, it will go through and build from source, and then it will cache them somewhere. And you can change the location where these binaries get cached. By default, it's going to be like on the same machine, but you can change that. So you could, for example, point to some file share or some other machine on your network, or some on-premises machine that in your organization that you have access to, and have all the caching going on there. Or you can cache it in one of the popular cloud storage solutions. So for example, you can use something like GitHub Packages to store your cache binaries. You can use Azure DevOps Artifacts. You can use Azure Blob Storage. You don't have to use Microsoft Cloud. You can use Google Cloud as well. And in fact, you can use any NuGet package feed, because we do support NuGet as a package format on the back end. So anything that acts as a NuGet package feed, you can use with binary caching. Now, this doesn't mean you can then pull those binaries and integrate them into some MS Build project, like by adding them as references in Visual Studio. That this is a different kind of NuGet integration that we're talking about. It's not using the NuGet tool itself. It's using Vcpkg. But the package format is the same, which allows us to just be able to reuse those feeds without having to come up with completely new feeds that would support Vcpkg. So that's kind of the thought process there. And the benefit of binary caching is, let's say you need to nuke your machine, start over. The second time you install everything, it happens in the span of a few seconds. It just downloads all the binaries and the sources. You no longer need to rebuild everything. Or say, for example, you want your development machine and your continuous integration environment to match. No problem. This is doable with binary caching. And you might have to go through the build from source once on your local development machine. then when you switch to CI, assuming it knows about this backend, it'll just pull it from there. And anytime Vcpkg is requesting to install packages, it will check the cache, see if valid packages already exist that match the build requirements that you have, and it will just restore those if possible. Otherwise, it will just update the cache with new packages that it builds on the fly at that moment. And so that's basically how binary caching works. And this feature has been around for a while, but I wanted to point it out as a nice way of saving you time, really, because time is the most precious resource in the world when it comes to dealing with C and C++ dependencies. And in fact, if we go to the ISO C++ surveys, I think the number 2 most common problem that people had was build times. So if you can build less frequently, that's probably a good thing. All right, so second feature is something called manifests. This is another feature I'm really excited about, and it also ties into the next 2 features I'll talk about, so that's why I want to talk about it now. Manifests are a way to declare your dependencies in a file. It's a JSON file. It's called vcpkg.json. And you can check that into your source control. So it's really easy to persist the state of what you want your dependency graph to look like for your project. Now, historically, the way you would install libraries with Vcpkg, and this is something we now call classic mode. You can continue doing this, where we'll continue to support classic mode. We have nothing against it. It works great. But the problem with it is that you have to kind of go into the terminal and say things like, okay, vcpkg install boost and rapid JSON and OpenSSL and all these other things. And if you have to do that manually, that's not always fun, especially if you have to do it multiple times in different environments. Some people get around it by writing something like a shell script, which you can just run, and then it will go ahead and execute a bunch of vcpkg commands and set up an environment. But then you have to maintain that script. Somebody has to write the script. Manifests are a way of just bypassing that altogether. You just write your dependencies in the manifest and just let vcpkg go from there. You can actually just say vcpkg install with no other arguments, as long as you're in the folder which contains a manifest, and it will go ahead, it will read the manifest, and it will do everything to get everything set up at that point. Now, manifest mode does work a little bit differently than classic mode, in the sense that with classic mode, libraries get installed in a subfolder of the vcpkg installation directory. With manifest, they actually get installed in the subfolder of your project, wherever that vcpkg.json exists. In fact, there's a file, or sorry, a folder that's called vcpkg_installed, and under there you will find the sources and the binaries. That's where they'll go. So that allows you to kind of keep everything with your project, which is nice. So you have your manifest, which declares all your dependencies, and you have your actual dependencies themselves, which live with your project. And I should call out that manifest works specifically for MS Build and CMake. We do want to continue expanding on the support, but those are the 2 environments the 2 build systems that we currently support. And in terms of using them with these build systems, with MS Build, you really just have to turn on the project property for using vcpkg manifests. And then once you've done that, it will just work. Whenever you do a build in MS Build, it will actually first check with vcpkg if any packages need to be restored. It will go ahead and do that, and then it will go ahead and build your actual project. With CMake, it's also pretty straightforward. So as a general rule, in general, when you're using vcpkg with CMake, there's a CMake toolchain file that we provide with vcpkg. You have to make sure you link that into your CMake. And as long as you've done that, then it's simply a matter of being able to just reference the individual packages in your CMake list.txt files. Usually that's just saying find package and then the name of it. And then you have a target link libraries function as well, and list your libraries there. Some libraries might not necessarily support CMake, and then you might have another extra step, or maybe you have to point to like the include path and where the libraries are, but it's really just like adding an extra line or 2. But basically what I'm trying to say here is we're just using existing CMake mechanisms for finding stuff, and then it should just work. And the benefit then is once you have this set up with CMake, when you run CMake configure to generate the cache, it will invoke Vcpkg. It will basically run Vcpkg install with no parameters. So it will look at the vcpkg.json and just set everything up. So that's basically how that works. Since vcpkg.json is something you can easily check into your source control, it makes it really easy to maintain consistency across your development team, making sure everybody installs the correct things. You can specify what you want and persist it in a way so that you don't have people installing the wrong dependencies. And you don't have inconsistencies as well between your development environment and your continuous integration environment, because you presumably want consistent, reproducible builds. And this was a way to ensure that. One other thing I want to call out about vcpkg.json, if you are contributing to the vcpkg project, you will care about vcpkg.json as well, because in fact, this is used to specify metadata about libraries that will be consumed with vcpkg. So we have something called a control file that we've used in the past. This is now deprecated. We're using vcpkg.json to also identify libraries that will be part of the vcpkg catalog. So just to identify things like, okay, what dependencies do those libraries have? And so that this is just information that vcpkg can then leverage by consumers of vcpkg. So it has all the information about all the libraries and the overall build graph. So I'm not going to go too much into that, but that's something you can find out more about if you go through our documentation. And this is just a basic example of what a vcpkg.json file looks like. There's a name kind of for the project that corresponds to this vcpkg.json. So that's the project you're specifically working in, and as well as a version for it. Version string is actually mostly used. You can basically put anything you want if you're consuming libraries of vcpkg, but if you're producing libraries, then that was actually like the version for the library you're producing. And then what are the dependencies that you need? So you basically just list all the libraries you care about, and you're good to go. That's it. It's like running vcpkg install, cxx, opts, fmt, and range v3, but this is just specified in that file. Okay, and then if you have if you're doing it on CMake, again, CMake list.txt, you can just say find package for all the different packages, and you have a target link libraries line at the bottom as well, which sets everything up. And then everything should just work. You run CMake configure, it invokes vcpkg behind the scenes. You don't have to do any additional work. vcpkg will be active and being used as needed to restore your dependencies. Okay, so now for the first announcement of this talk. So we had another feature that was experimental called versioning. And we're happy to announce that this feature is now generally available. We're considered to have moved out of experimental state. So we're very excited about that. This is one of the most popular features we've been requested over the past couple of years. What this lets you do is to lock down on your preferred library versions. So remember when I said that vcpkg, the catalog exists as one version set, and the downside is you can't really pick and choose your own versions? Well, actually, I lied. You can. You can use the versioning feature to do that. So by default, if you do nothing, you will still just get whatever version is in that version set, but you absolutely can declare your own versions. So you do this in the vcpkg.json file. It only works with manifest mode. And there are three configurations you can make, I guess, as part of that. And I'm just going to quickly call them out. The first is something called built-in baseline. This basically establishes a default version for all the public dependencies. Think of this as the version set that you're starting off with, right? So if you're not using versioning, this will just be like whatever the most recent, whatever version of vcpkg you currently have installed on your machine. It will just be using everything from there in that version set. But you can set this to something else. The second thing you can set is something called the minimum version. So this is useful if you want to say, well, actually, I want a greater version than my baseline. I don't want to be just on the baseline. So if you want to say, okay, I want at least this version of library, you would say, you would use version greater than or equals to say that you want that. And what this will do is it will typically give you exactly that version that you asked for, but it may go a little bit higher if vcpkg detects that actually your build will not work because there's some incompatibility based on the version you picked and what your overall build graph looks like. If that is the case, then it will increment that and it will go to the next higher minor version that it can successfully build. And that's basically how that works. So it's kind of like saying, I want this version, but I'm flexible. Like if you need to go a little bit higher, you can do that. But sometimes you might really say, no, you really need to use this specific version. Don't change it. Do exactly what I tell you. And that's where overrides comes in. So that lets you essentially say, I want exactly these versions of these libraries, and you can use that. This is particularly useful when you want something that's really like an older version. Then even the baseline overrides trumps everything. If you say that you want that, that's what you get. So that's basically how versioning works. This is an example of vcpkg.json file. It looks essentially the same, except you can see we have version greater than or equals for FMT. So we're saying we want at least that version. We'll typically get that version unless it won't build, and then it might give me like 7.1.4 if that exists. And then zlib is not doesn't have a version specified, which means that I'm just going to get whatever the default is in that baseline. So you don't have to specify versions for every single dependency, but you do need to specify that built-in baseline so that we know exactly like, okay, what is your default state? All right, so that's versioning. So then let's talk a little bit about registries. So registries is another feature. It was experimental. It's now generally available. We're really excited about that. This allows you to bring your own libraries to Vcpkg. This is a big deal. So Vcpkg has this public catalog over 1,600 libraries, but you can actually bring your own libraries. Or maybe you can have like a custom fork of an open source library because you don't want the default one. Maybe you have some additional security checks that you need to do. Maybe you did some patching and yet that hasn't been pushed upstream yet. Or you just have your own completely private library, completely isolated from the internet or from the open source world anyway, that maybe you're using within your organization. That's where you can use registries to help you. So there's a couple different configuration files that you can use to set up a registry, but essentially the way this works is it's like setting up your own Vcpkg catalog. Okay, you have a baseline that you can set up. You can define your libraries and the versions. You have a portfile.cmake, which is basically your build recipe. This is if you've authored libraries for Vcpkg, this is essentially the same thing. And you can specify, okay, what is the type of registry? Is it like a file system registry, or is it something that lives in a Git repo somewhere? Where does the registry exist, and what are the available packages? You still need to use Vcpkg manifest with this, or vcpkg.json. When you're producing libraries for, remember when I said when you produce libraries for Vcpkg, you still need vcpkg.json for that. You also have libraries for registries. So that's basically how that works. And that file, or one of the files used for registries is vcpkg configuration.json. So I wanted to call this one out because it's a bit different than stuff we've talked about before. So in this case here, we have a registry. It's a Git registry. So there's actually like a Git repo that you can specify that's under the repository section. Then you can list the packages that correspond to that. So that's basically how that works. All right. So I wanted to say a few things just in general about Vcpkg. So Vcpkg is an interesting case of a Microsoft product that from the beginning has been great for open source projects. Like if you have an open source project and you're using and you're consuming dependencies, Vcpkg is a great tool for that. And that has been the case from the beginning. What we haven't heard so much is Vcpkg being great for enterprises, which is really weird because we're Microsoft, so we're kind of expecting it to be backwards, right? Like, oh, we're great at targeting enterprise, but open source, I don't know. Can we do that? Can we make it work for open source? But since this started off as an open source project and we've been investing so much into it, I think the perception from the beginning in the community has been, oh, if you have an open source project, yeah, you should use Vcpkg. So that continues to be the case. We'll continue keeping Vcpkg as a simple solution for C and C++ dependency management with a lot of powerful features. It's also the case, if you're working on small projects, yeah, Vcpkg is great for that. Even if you only need, a couple of dependencies, just being able to save time on building those dependencies yourself, that's worth it. At any time you can save, it's absolutely worth it. But it's also the case that Vcpkg is great for education. I know that we have some students that for their coursework, they're required to not use any libraries because using libraries is cheating. You have to write all the code yourself from scratch. We don't really think this is the best model, and it doesn't really apply to the real world when you go and get a job as a developer. So hopefully we do see more students using dependencies to save a little bit of time and not rewrite things that have already been written many times by people in the past. But Vcpkg is a great tool for saving time. And we know if you're a student, you're really busy, and you want to save time on that, on setting everything up. So that's great. But we also want to say that with these 4 features we've added, Vcpkg is great for professional development. It's great for enterprise developers. That is a statement we want to be able to make. We know that all 4 of these features that I've talked about have been popular requests by people from all across the community, even for open source projects and for small projects. But there are a lot of professional developers that have told us, we cannot even start thinking about using Vcpkg until you have these features. Well, now we do have these features, so we want to be able to say, give Vcpkg a second look, try it out, let us know, is this something that works for you? And we're happy to make it better if it's not, but we are really excited with all the progress we've made, and we do think we have a pretty compelling solution now to managing your dependency needs. Whether you want to lock down on versions, whether you want to declare stuff in a manifest, whether you want to save time with builds, Vcpkg is a great tool. And last but not least, we now finally have a Vcpkg website. I'm really excited to announce vcpkg.io. For a long time, we've just been like a repo on GitHub. We started off with a small team, just working on this as a tool for migrating people to newer versions of Visual Studio, and we've grown way, way past that scale. We're targeting 3 platforms. We have over 1,600 libraries that we support. And of course, we have these features now that really give you a more compelling solution for controlling your dependencies and setting up your environment the way you want to. But we also thought, you know what, we need a website. I mean, everybody needs a website, right? So please check out vcpkg.io, whether you're new to Vcpkg or whether you're a Vcpkg veteran. We have a number of useful things on the website. You can learn about Vcpkg, of course. You can follow the getting started instructions. We have our documentation there as well. You can actually, let me actually just switch to it. So this is what the website looks like. Again, it's live right now. I want to specifically call out the packages page. Okay, you can actually browse for packages. So you can actually say, you know, does Vcpkg have the libraries that I care about in the public catalog? Well, now you can search. You can just go ahead and look for stuff, and you can see exactly what is available. So that's something that that can be pretty useful. Like I'm going to use SQLite as an example. You know, we have a couple of different options for SQLite. You might be curious to know what are the options that are available. And if you want to see, okay, how do I actually install this? So assuming you're using classic mode, you know, you can just copy and paste this from here. So it's very, very straightforward. Do check out our website and let us know what you think. All right, so that's basically it for this talk. Again, if you want to get started with Vcpkg, check out vcpkg.io, which is now live. We are always looking for feedback. If you try out Vcpkg and you find something that doesn't work very well for you, please feel free to interact with us on GitHub. You can file an issue if you find like a bug or something that's just broken, or if you want to have new libraries added to the ecosystem, at least to the public catalog. Of course, you can always add your own to a private registry if you want. Please go ahead and do that. We also have a discussion forum now on our GitHub repo. So if you want just general discussion about Vcpkg, or if you're stuck, you have questions, please feel free to engage with us there. We're happy to have you. And well, again, I want to thank the Vcpkg community that has contributed so much to this project and made all of this possible. Thank you.
Thanks so much, Augustin. Okay, we've got a bunch of questions in chat. If you have any other questions and you're watching on Twitch or on YouTube, please head over to Microsoft Learn TV, which is where you can ask your questions. If you ask questions somewhere else, we won't see them and they won't get answered. So if you want questions answered, go to Learn TV. Okay, so one question is, will Vcpkg be distributed as part of our next, as part of VS 2022?
So yes, we are actually working on shipping Vcpkg as a binary that can be distributed with Visual Studio as well as Visual Studio Code. We do expect that to land in the Visual Studio 2022. We've done kind of the groundwork for being able to ship it as a binary. There's a bunch of like security stuff and compliance stuff that we have to do. And right now, for those who don't know, the way you install VC packages, you have to clone the repo, and then you run the bootstrapping script we provide to build it. But by being able to distribute it directly as a binary that you can easily download it and get started with, this enables us to integrate it with other environments. So we absolutely will be shipping it with Visual Studio. It'll be included if you're using a C++ workload, a Visual Studio Code. Right now, we're thinking we'll probably have like a separate extension you can install for Vcpkg. But yeah, we are absolutely doing that.
Cool. Before I go into the other questions, if you're on Learn TV and you go into the announcements section, you'll see the resources which Augustin just posted. Another question is there any plan for Vcpkg to use custom private repos? I think we answered that with our with the talk already. But then there's another question down below, which is, can versioning be used for public libraries, such as for installing a specific boost version? I think that's something you covered in the talk as well, right?
Yeah, so versioning does work with that. You may not be able to get every single old version of a library. If you need something that's not already currently available in the catalog, you may have to set up a custom registry for it. But going forward, we are expecting that every library that is updated, you'll be able to install any of the previous versions. So you don't have to worry about, this was another problem people had with Vcpkg, was we would update the versions, but people really wanted to stay on the old version, and then they updated Vcpkg, and now it's like updating the version. So with versioning, you don't have to worry about that. Yeah, you'd be able to stick to that version. The worst case, if a particular version is not currently provided there, you can set it up in a custom registry.
How about installing an older version through the command line instead of via vcpkg.json?
We do not currently have support for that. If you feel really strongly about that as a feature, please feel free to start a discussion thread with us on GitHub. We would love to hear your feedback. We just prioritized vcpkg.json because we kind of saw that as the future of just managing dependencies of vcpkg. There are a lot of benefits to using vcpkg.json, but we do understand, of course, that the classic mode has been around for a while. We will continue, of course, to support it. So yeah, please let us know, and we can have that conversation.
Cool. And then on the other side of newer versions, what if there's some like publicly available new version, like OpenSSL gets an update, but the Vcpkg public repo hasn't been updated to pull down the most recent version which is available? Do we have something to help out in that scenario?
Yeah, so again, that's something you can set up with a custom registry. So we do have a pretty active repo. We do get a lot of PRs with updates to libraries. So hopefully we don't get too out of date for too long with anything. But if you do really badly need the latest version of a library and it's not currently in Vcpkg, you can always set it up with a registry. Again, like a lot of these features have been set up with flexibility in mind. We recognize that the default experience, if you do nothing, might not be flexible enough. Maybe you need to make some changes. With things like registries and versioning, you can go in and customize your requirements as much as you want.
Cool. And then there's a question about automating patching. Like if you have some custom patches that you want to apply, but don't necessarily want to like have your own fork of the library. What's the story with Vcpkg there?
So really, like your options are, if it's like an open source library, you can contribute to the Vcpkg public catalog, and then you can make use of that, and then everybody else in the community can make use of that. Or you can set up your own registry, which would require doing the additional legwork of figuring out, okay, how do we actually compile this library and listing it out and listing the available versions and stuff like that. Those are the current options that are available. We don't really have anything that's in between that. Again, if you have any suggestions for us on how we could improve the experience, please start a discussion with us about it.
Cool. And then this question on maintaining in-house patches for public libraries. I feel like we've covered that with these answers so far.
Yeah, like a lot of the answers I think come back to registries. I will also call out that we are actually working on something like this. So we're actually working on rolling out Vcpkg across Microsoft. When I say Vcpkg is enterprise ready, I'm not just saying that for the sake of some marketing messages. We are actually working with a lot of teams across Microsoft to set something up. And one of the workflows we will have is they're not going to be pulling dependencies directly from the public catalog. They will have like a mirror of it that's controlled and has custom patches and security patches and stuff like that, and security checks, and passes all the compliance requirements. And that also has like business continuity in case the developer behind an open source package removes it one day. You don't want everything to just break. So that's a workflow that's being set up using Vcpkg, using versioning, using registries to control the environment.
Cool. So next is CMake a requirement to create VC packages?
Yes. So that's just the workflow that exists today. It is CMake based. That was just a design decision that was made since CMake is very popular in C++. I know Conan, I think, is more Python based, although I'm certainly not an expert on Conan. So Conan and Vcpkg are kind of the most popular options available today. So yeah, if you want to author packages, then you would have to do it through a CMake way for Vcpkg, and that's what we support today. Again, if you have suggestions for us on alternative ways we could do it, please feel free to start a discussion thread.
Right, but your project build system internally isn't required to be CMake. Like you can trigger off some other build system internally.
Yeah. So to be clear, I'm talking about producing libraries with use for Vcpkg. If you're consuming libraries, no, you do not have to be using CMake.
Can we talk about automated port publishing for libraries which are published via Vcpkg? Things like automated pull requests for opening new tagged versions in GitHub.
That is a great suggestion, and it is something we've talked about a little bit in the past. We've been thinking about things like using GitHub Actions to automate some of this. We're still in early stages exploring what we could do. We definitely want to continue improving the process for updating ports. We know we receive a very large volume of PRs, and we spend a lot of time processing all those PRs. So it certainly benefits us as well to be able to automate as much of it as possible. So we're continuing to work on our CI process and our automation process. And just stay tuned. I guess you should see improvements gradually over time.
Great. All right. Well, we're pretty much exactly at time now. So thank you so much, Augustin, for your time and for this talk. I hope you all learned something new about Vcpkg and how that can help you out. So see you later, Augustin.
Thanks for having me.
Cheers. Okay, so next up, since we've all been sitting down for quite a while, at least I have, we're going to have a short stretch break. So we've got a little video to show you of some stretches you can be doing.
Hi, I'm Daniela. Let's give our shoulders a stretch.
Hi everyone, my name is Erica, and my favorite stretch is a neck stretch for when you're sitting in front of a computer screen all day long.
One stretch I'd recommend for sore wrists: hands out like this, up, relax, make a fist, and down. And then repeat that 5 times. Okay, I hope you all had a stretch, had a stand up. Someone came to join me. This is Marshmallow. He says hi. He's very soft and fluffy. And he's just, yeah, he's a lump of fluff. But he's very cute. And he likes to come up and annoy me when I'm in calls or running conferences. So if you want to say hi to Marshmallow, you can do so in chat. But our next talk is going to be on code analysis, both dynamic analysis and static analysis. So Sunny Chatterjee and Jim Radigan are going to be telling us about all we've been working on in code analysis and how it can make your C++ better. So welcome, Sunny and Jim.
Thanks,
hey. How's it going?
Good. How are you?
Good. I've got a little friend now, so I'm happy.
That's great.
So yeah, thank you very much for your time and joining us, and I'll pass it over to you.
All right.
Bye.
Hey, everyone. My name is Sunny Chatterjee. I'm an engineering manager in the C++ team at Microsoft, where I'm lucky enough to work on static analysis. And today I'll be joined by Jim Radigan. Jim is an architect in the C++ team, and we'll show you how you can use code analysis to empower developers write performant, reliable, and safe C++. Hi, Jim. All right, looks like you're muted there.
Good morning.
All right. I'll cover the topics for today's talk. First, I'll go over why code safety matters. And then I'll talk about how you can improve code safety using static analysis principles. And Jim will go over how you can use address sanitizer to improve the safety of your code. So why code safety matters? So in 2020 State of Quality Survey, developers were asked what sort of analysis tools they are investing in to improve the reliability and safety of their code, essentially making their code safe. And both static and dynamic code analysis tools topped that list. So the challenge for us was to see if we could leverage the code analysis tools that we work on here at Microsoft to make C++ a safer language. So in this section, I'm going to focus mainly on static analysis and how you can improve the safety using static analysis principles. So what is static analysis? It's a pretty simple technique that reads C++ code, applies some clever algorithms to look for defects, and reports these defects at compile time. And so why static analysis is a pretty popular technique is because it can drive your quality upstream, where you can find bugs at the very beginning of your development cycle. And that saves a bunch of dollars for the company. And large corporations, they love it when people can save dollars, right? So it has been in use in many large corporations over the years. It has a pretty minimal overhead in terms of there's no implementation needed. There are no test cases that you need to write. And it has, a pretty strong, it has a proven track record in finding a pretty wide range of issues in your code, ranging from correctness, performance, reliability, safety. So you can find all these issues using static analysis. Next, I'm going to show you a few good checks. For long, people have thought about static analysis as lin-style checks. And what I'm going to show here in these examples is, static analysis has evolved over the years, and you can find a lot of deep semantic errors in your code using it. And it's a lot more than a classic lin-style check that you would expect it to be. So here is an example where you have a function unchecked index. It takes a vector, a reference to a vector. Then you get an index from the while. So you don't know anything about the range of that index. There's a function called getIndex that gets you that index. And then you're basically dereferencing into that vector, but you don't know whether you'll be accessing that vector out of bounds. So it's a pretty simple check to write here, that would say, use GSL add instead of unchecked iterator. Now, GSL add, for those of you who are familiar with the guideline support library, you know that it's like a function that would terminate your program if you're trying to access this container out of bounds at runtime. So because of that runtime safety, it's a much safer alternative to use. Let's look at a slightly modified example. In this second example, the index is in fact checked, because you can see that if the index is less than the size of the vector, only then we try to access into the vector. And so this is a perfectly valid access. And A smart static analysis tool would be able to, walk these paths during analysis and figure out all the conditions. And so it would kind of be smart about and not warn in this particular example. So as you can see that, it's not just a simple lint style check, but there is a lot of deep analysis happening under the hoods to kind of provide you with high quality defects where you actually have a bug in your code. In the second example, I'll show you how you can use static analysis to make your code more performant. So you have some struct here that has a large struct in its body, and it has a method that returns a const reference to that large struct. And then you have a function foo that essentially calls get large struct, which returns a reference. C++, as you know, is a copy by default language. So when it gets assigned to that auto variable, that large struct gets copied. And because of that, there is a lot of, that's not a very efficient way of writing code. So a static analysis tool can help you here and tell you that, hey, there is an expensive copy happening here. You should use a reference. However, let's look at the next two lines. In the next two lines, you can see that we do get a reference and it's copied, but there's also the data inside that struct that's being mutated. So we are writing to its field the value of 43. And so in this case, a copy is in fact necessary. Again, a smart static analysis tool would be cognizant of this scenario and would not ask you to create a reference in this particular case. We need a copy here. The third example is where you're actually calling some struct which returns a temporary object, and you're calling get large struct on that temporary object, and then you're assigning that to an auto variable, which means a copy here is happening. And again, the smart static analysis tool would figure out that the copy here is necessary. Why? Because the lifetime of that temporary object is not extended past its statement. So a reference here would mean that you would run into lifetime issues after this statement. So that's my second example. For my third example, I'll show you how you can use static analysis to prevent concurrency errors. Here is an example function called mutex acquiring generator. It acquires a lock, and as you can see, the variable is marked with a guarded by annotation, which means you should be acquiring this lock before, in fact, you access this variable. Then this coroutine yields its control before it relinquishes that lock. Now, the problem with this is, imagine there is a second thread that picks up this coroutine and then it tries to get that lock. And this would be a classic deadlock where the first thread has return control while holding the lock, while the second thread is waiting for that lock. Static analysis can help you here. It can tell you that, hey, you're suspending a coroutine while holding a lock, and that can cause deadlocks. Don't do that. So this is another interesting example where, as new language features evolve, you can see that you can make mistakes in new ways, and static analysis can be a powerful tool in guiding you in writing code that is correct and safe. My last example is a lifetimes check. Lifetimes, as you know, is a 40-year-old problem, as Herb often refers to it as. And you can use static analysis to also find issues about lifetimes. Here is an example where you have a dangling iterator. There's a vector, 3 elements. You basically take an iterator to the beginning of that vector, and then you're accessing, dereferencing that iterator. And that's perfectly valid code. It should be overriding the first element with 0. Now, let's look at the second dereference here. Here, you're basically pushing back another element onto that vector and dereferencing through that stale iterator again. And that's not OK, because when you do a pushback, the memory layout can change. So that first iterator you had pointing to the beginning of the vector can point to invalid memory. So if you run static analysis here, it can actually point you out that, hey, don't dereference this pointer because it's invalid, and it will tell you further that it's been invalidated in the previous line. So those are a few examples of a few good checks that I wanted to cover today. Next, I wanted to give you a glimpse of how the static analysis platform looks like. Just an under the hood picture here. I'll be quick on this for the scarcity of time, but you have C# front end. You have the parsers parsing these files. It ensures that it has valid syntax. It produces something called abstract syntax trees, or ASTs, that represent source code. And then you have something on top of it called prefast. Prefast is this analyze, as you know it in MSVC. basically loads and unloads its own plugin extensions. It calls back to each plugin as declarations and definitions are parsed, and then it also emits defects it gets from its plugins. On top of FreeFast, we have something called ESPX Engine. So ESPX Engine, what it does is it processes the ASTs to simulate function execution. And the way it does it is by converting these ASTs into something called control flow graphs, or CFGs. And as it tries to simulate the function execution, it invokes callbacks on each of its own extensions as the simulation proceeds. So you have one extension which handles its own callbacks of interest. It tracks some properties that it's interested in. It detects errors, and then it reports its defects back to the engine. Similarly, you have a second extension that handles its own callbacks and detects errors and reports them back to the engine. ESPX Engine is a pretty powerful platform. It has evolved over the last 10 years through collaboration between DevDev and Microsoft Research. It has a lot of good, useful libraries like symbolic state tracking. It has a fast theorem prover. It has alias analysis, loop widening. All of this makes it a pretty powerful platform to do data flow and path-sensitive checks. And a lot of the deep semantic checks that I showed you in the previous slides, they are powered by some of these libraries sitting on top of ESPX Engine. I would like to, tell all of you to join the fun. My key message today is, we have been using static analysis at Microsoft for nearly 2 decades, and it's validated millions of lines of production C++ code. It's available in all editions of Visual Studio. It's, static analysis finds bugs, it's free, and therefore you should use it. So what's next for the static analysis team? We definitely want to invest in C++ code safety checkers going forward. We also want to be able to meet the tooling needs of the community as the language evolves. So for C++ 20, for example, there were a few interesting types added for static analysis. Standard span would be one of them. Similarly, coroutines was another language feature where you could create new kind of lifetime problems when you're using coroutines. So as the language evolves, there are new ways people can make mistakes, and static analysis tools, any tools for that matter, should be constantly evolving to catch new kinds of defects that you can introduce. We also want to focus on improving our diagnostics. No matter how smart a check you are writing, I think for a tool, diagnostics is very important. You should be able to point out issues in the code that you're writing. The issues should be easily understandable. It should give you a glimpse into what's the reasoning behind the tool. So we definitely want to focus more in improving our diagnostics going forward. And we also want to have a tighter integration with developer workflows. So I think our friends in the IDE team did an awesome job integrating these checks as part of the Visual Studio design time experience. And we also realized that the developers are also spending time in GitHub, they're spending time in Compiler Explorer. So the point here is we would have a static analysis experience available for developers wherever they come for writing C++ code. In the end, I would kind of urge you all to give us feedback and suggestions. It could be about a bug, a feature request, some new checks. We have a pretty active community in developer community. A lot of our prioritization is directly based on the feedback and suggestions we receive there. So I would urge you to keep the feedback coming. For example, if you would like us to, open up the static analysis platform that I just showed you in the previous slide, and if you would like to write your own third-party plugins, that's something you could probably reach out to us and suggest in the developer community. Definitely helps in the prioritization. In the end, I would like to leave you with a few useful resources. Our documentation is at docs.microsoft.com. It's not perfect, but we are constantly looking to improve on it. Feel free to suggest improvements on the documentation and check them out. We also have our team blogs. Most of our announcements are made through the team blogs, and I've just had 2 blogs listed here that highlight some of the work that went into the static analysis tools over the past few months. So definitely stay tuned for our announcements in the C++ team blog. And there is some additional reading that I would like to leave you with. The C++ core guidelines is a great resource to check out. It has a whole bunch of rules on how you can write modern, safe code. And one of our checkers, the C++ code check, implements a whole bunch of rules from this guideline. We also have a guidelines support library. It's a GitHub repo that we maintain where we implement a bunch of type extensions, which are used to enforce some of the core guidelines. So definitely you can engage with us in the GitHub repo by contributing to Microsoft GSL. And we love all sorts of static analysis tools. And for those of you that haven't played with ClangTidy, we have got ClangTidy integrated inside of Visual Studio. Definitely check it out, and you can read more about ClangTidy in the LLVM org. I would like to end with a demo because so far I haven't shown you anything what the experience is in GitHub, is in Visual Studio. So let me show you an example in Visual Studio how static analysis is integrated. So here is a source file, and you can see these green squiggles sprinkled through the source files. Essentially, what happens is as you're writing and typing your code, static analysis runs in the background, and the defects show up as green squiggles. So if you hover over the squiggle here, it will say, oh, the default constructor may not throw, declare it as no except. Similarly, you have another squiggle here that says, function work with delete can be declared no except. If you have a squiggle here under delete, it says do not delete a raw pointer that is not an owner. For those of you that are familiar with core guidelines, you know that only owners can delete its own memory. And it also says avoid calling new and delete explicitly, use unique pointers, because that way you can write memory safe code. So there is a whole bunch of static analysis issues that you would find available in your project as green squiggles. As you fix them and save your work, they should start disappearing. One interesting thing in this demo is there is a subtle memory bug here that I don't see mentioned by static analysis. And so there is a magic button that I would like to show you. If you go to the project properties here and go to general, there is the drop down, this magic drop down, as I call it, called enable address sanitizer. And all you got to do is flip it to yes and save your project properties and recompile. And once you do that, you will find that address sanitizer is able to find all sorts of subtle memory issues in your code. And to talk more about it, I'm going to hand over now to Jim. And Jim is going to talk about the magic behind this address sanitizer. Over to you, Jim.
Hey, thanks, Sunny. Great job talking about the static analysis. Good morning, everybody. I'm just going to take that same demo that Sunny was showing you. I named it after him. I just wanted to show you the code. So right here, I just added the one-line pass to prove that this thing will actually run. So I'm just going to compile this in an ordinary way. Now I'm going to run it. And you can see that that ran, and that's after you would have taken care of some of these static analysis bugs. What I'm going to talk about is the address sanitizer, which is going to be about dynamically finding these bugs at runtime. So in order to invoke the address sanitizer on exactly the same example that was Sunny was showing you, I'm just going to type cl-f and address. We're going to add some debug information so that the stack walker can handle this when it finds an error. Now, when I run this, we're going to get an error. And the error that's pointed out by the address sanitizer is that there's a new delete type mismatch. And this is the standard output that you would get from the Clang compilers. So what we did is we took this a step further and we integrated this tightly with Visual Studio. So what I want to show you is if I pull this up in the Visual Studio debugger, we'll get what I consider to be an easier read on what the problem would be. So if I just click go, The integration with Visual Studio has popped this error in the window for you. You can actually see that it just says the deallocation size is different from the allocation size. And you can see that it happens exactly right there. And now you have your call stack and all of the information that you would have had from the command line behind this window. But this is a lot easier to read. And so what's happening here is the address sanitizer found out that there wasn't a virtual destructor for the base class that could be overridden. So that's why the delete had a mismatch in sizes for what was allocated, because right down here, we actually put a derived into the pointer B, and then we passed it down to the delete. So now, what I wanted to do was show one more feature that we added for supporting this, which is, I think, really important. You set that environment variable, asan save dumps. What's going to happen is when this thing errors, it's going to save a new type of a dump file that has a whole bunch of asan metadata in it. And the IDE has been engineered to parse that and display it. So if I run this now, same file, it's got an error. But what it's doing is it's saving that dump file. And now I can actually look at that file offline. So if you're doing stuff in the cloud, what you can do is set that environment variable, store all of these dump files in a database, and come back and process them whenever you want, because all of the metadata has been saved, and this can be rehydrated by Visual Studio at any time. So if I just open this file with Visual Studio, one more mouse click, and boom, I'm processing this bug offline. And the number one thing that's really significant about this and these dump files is that this changes the way you would report bugs, because with the address sanitizer, there are 0 false positives. So if you have a bug, it probably is yours. And with this dump file, if you stored this with your bug reporting database, it's extremely accurate. You have memory, you have the registers, you have the call stack and all the symbols and the source code right there. And if you want, you can even go to the disassembly and you can see where the code, where the derived was created, and you can also go to the code for the delete. So with the combination of integrating this tightly with Visual Studio and with creating these dump files, we feel that we've really made the address sanitizer as useful as possible. And the reason for that is that the memory safety issues that the address sanitizer focuses on are dominating what all the CVEs are every year. And as we continue to develop more and more code with C and C++, we continue to introduce these memory safety issues, and it's a really big deal. So if you want to consider this for just basic correctness, the address sanitizer is a big help. Or if you are worried about security and third-party nation states, this is one vulnerability that is constantly exploited. So Sonny was talking about static analysis, and that's meant to be used at build time. That's low overhead and it catches bugs really early, but there's some noise and warnings. The address sanitizer is done at runtime. It requires a separate build. There are 0 false positives, but it finds bugs that any type of static analysis can't find because of cycles in type propagation and alias analysis. So from our point of view, both of these are available under one compiler switch, and together they present what we consider to be a defense in depth. And this is, I think, very covering for a lot of the problems that you see in the industry today, the combination of these two. So why is it that there are things that static analysis can't find? And what I'm going to do is provide 2 key insights to clarify. So one core issue has to do with the language definition itself. So in C++, there's actually a conceptual cycle between type propagation and alias analysis. In that one simple yellow text, if I don't know what the type of the pointer P is, then at compile time, I can't figure out what that call is to, and therefore I can't figure out what the effects are going to be on the alias analysis for A or B or anything that A and B contain pointers to. And then if it's difficult to find that what P's type is, it's probably because there were other pointers that aliased P. And so you can see the only way this cycle can be broken is at runtime. Here's the second core insight. This is an example of something we call secure by coincidence. It's secure because this program will run no matter what, and it's because of basically the implementation of malloc on the platform. So if malloc allocates things that are 0 mod 16 in size, and then you get a buffer of space that you're unaware of, and if you overflow that, your program will still run. In this particular example, the red less than or equal to in the header of the for loop is where the error is. We're going to write one more character. So if size is mod 16, the final write to local will corrupt stack data. Other cases will only read or write to malloc slop. This will only be observable if the following page is unmapped or not writable. And it will also be observable on the use of the corrupted data. All other cases are silent. So this is a platform runtime dependent issue right here. And this is another, if with alloc A, this is another really great exploit. Before I go any further, I want to acknowledge Google for creating the address sanitizer runtime. And I want to say a special thanks to Konstantin, who led the team at Google and has been very successful in taking the address sanitizer forward with fuzzing. It's been an amazing growth in the industry, and the address sanitizer really has become a de facto standard. So before I go any further, this is what I would say is a concise definition of memory safety. Now, all of this is documented on the MSDN page, and it's really complex. If you go into each one of these examples in a presentation that's this short, I'm going to leave you with the documentation, and a lot of these titles here will get you to examples on the MSDN page, and every one of these types of errors has source code as well as a Visual Studio screen dump. So the goal by using the address sanitizer is that there are no memory safety bugs left in your application, but it's always done with 0 false positives. If this thing finds a bug, it's probably your fault. So this is what the Clang and LLVM output looks like on the command line. And I'm going to go back to the demo just to make sure everybody understood what I was showing. We took it to this step. And with this IDE innovation, what we did is we tried to change the debug experience. And we also tried to change the way people should report bugs because of these new crash dump files. You don't have to use words to describe anything. All you have to do is pass along one of these new snapshot files, and Visual Studio will actually rehydrate it just as I've shown on the screen. So here are some of the results, and we're just getting started. We went after open source. We found bugs in the Azure SDK, Boost, OpenSSL, and the Electronic Arts version of their STL. We found 0 days in Windows. We also have a continuous fuzzing team, which uses the address sanitizer and then puts your modules into a wrapper, which will randomize input continuously, looking for all the paths of execution to exploit. We found bugs in the Visual Studio shell itself. We found bugs in the VS debugger. We use it on the front end, the back end, and the linker, and we found bugs across all of those. I went on site to a couple of customers and found bugs in their code. And right now, we are bringing up Office, which is a giant source base with a lot of legacy code, and it's difficult to successfully build. But we did a manual boot of Word, PowerPoint, and Excel, and we found one bug in each of them on startup. And after this talk, I'll be talking to the Office team about integrating this into their build and dev process. So we use ASAN and static analysis. They both find bugs. And what we're saying to you is that you should too. And that's about it for me. And if you have any questions for Sunny or I ended a little bit early just to make sure there'd be time.
Yeah, perfect. Thanks so much. Yeah, we got a few minutes for questions. So if you have any questions, make sure you're on Microsoft Learn TV, because we will not see any sent to YouTube or Twitch. And then drop them in the chat. So we've got one question here. When you load up a dump file in Visual Studio, do you have to manually make sure you're using the same code you used to compile, or is there some magic which will do that for you?
Yeah, you do. You have to have the debug symbols in the code. We're working on expanding that so that it's rad hardened. So with Git, it'll all automatically pull down the correct versions. Cool.
And then a couple of questions which Gabor did answer, but I think would be interesting for the video is if you're trying to introduce these analysis tools into a large existing code base, what would be your tips?
Well, I can speak for the address sanitizer, and the address sanitizer is done so that you can do it a step at a time. The only prerequisite is that the C++ file that contains main has to be compiled with the address sanitizer flag so that the runtime can get ahead of everything in your application to hook all of the allocators. After that, you can run other modules that haven't, with that, or libraries that have not been compiled with the address sanitizer, and that's because a lot of the shadow bytes that we use, and I didn't have a chance to talk about that, will, quote, fail open. In other words, it doesn't require everything to be compiled with the address sanitizer on. And Sunny can speak to the static analysis.
Sure. For static analysis, I would say the first and foremost tip for a large code base is to grandfather existing warnings so that developers only get to see what they're working on. There's a lot higher reaction to the warnings when you're working on a PR, for example, or making a code change. So showing relevant warnings, not including warnings from external components, not including warnings from pre-existing code, legacy code, definitely increases the chance of these warnings getting attention and getting fixed. So I would say, and also having these warnings show up at every point in the developer workflow, whether you're just writing your code, or you are compiling, or you are even when you spin off a PR. I think at every point in your dev workflow, we got to have these checks, and we got to show you the relevant warnings. And with that, we have seen people pay more attention, and issues get fixed, as opposed to code gets checked in, and after 30 days you find bugs. I think people forget it's not in their top of the stack, and so we have seen the former approach to be a lot more effective.
Cool, thanks. All right, so there's a few more questions in chat, but we're pretty much at the end of our time here. So Sunny and Jim, if you want to hang around and answer those questions in chat, I'm sure people would appreciate that. And we're going to move on to the next talk. So thank you so much for joining us and giving us your expertise. Thanks. And we're going to move right on to the next speaker so that we finish on time. So our closing keynote today is Gabriel Dos Reis, who's going to tell us about C++ modules in the year 2021. Hey, Gabby, welcome.
Hello. Hello from Seattle, or Redmond, I should say.
Yeah, it's great to have you closing out the conference. Did you close out the conference again last year? I can't remember. Wait, you had another great talk last year, but I can't remember which session it was.
I think that must have been at Meeting C++ 2020. Yes, it was closing keynote.
Yeah, cool. Well, thank you so much. And everybody, Gabby.
Yeah, glad to be here. Okay, so I want to just give you a quick update on where we are with C++ modules this year 2021. So you probably already watched Daniela's talk. If you haven't, please do right after my really go and watch her talk. It's fantastic. Let me give you a quick 30,000 feet above view of what modules are. Essentially, they're language constructs that allow you to clearly specify the interface of your components. So here I have basic component that gives you a rectangle. I call it modules basic plane figures. I have a point, have a rectangle, and then we have utility functions that give you the width, height, and an area of a rectangle. So with modules, you can just specify directly what is needed for the consumer of your components, and this is it. Simple. And how can you use this stuff? Equally simple. Instead of having some kind of include file, you just say import the module name, and then you proceed to write your code as if that import had been some include. So those two things are the basic things that you need to know about modules, nothing else. How this actually gets compiled depends on the compiler. Each compiler has its own flags and so forth. But this basic semantics at the C++ level is quite the same. So what are they really? They're a C++ 20 features. What do they give you? They provide you componentization. You can, as I showed earlier, you can delimit very clearly the abstraction boundaries of your component. Here, when I say export module basic plane figures, I'm saying explicitly I want points, the types points, rectangle, and the three functions to be usable. If I've had declared any other functions here that wasn't at all preceded with the keyword export, that function will not be usable from the outside. So you have a language means to say these are the boundaries of my components. They give you isolation primarily from macros, evil macros. With named modules, if you define a macro before you do an import, that macro, its existence is not at all observed by the boundaries, within the boundaries of your modules. And similarly, if you happen to use macros, God forbid, you happen to use defined macros within your named module, they will not be seen from the outside, which is good. The third is because modules bring this kind of structure, it makes structure available to the compiler to exploit. So you benefit from the hygiene, you benefit build throughput. In some of the testing I've seen, speed up varying from 5 times to 10 times. And yesterday, a friend of mine was actually showing me a program, real world program, where he got 42 times, not percent, 42 times X factor speed up. So that is what modules bring you. And the fourth thing that they gave you, which is quite interesting for C++ in the modern era, is that now you get to enjoy semantics-aware developer tools. An example of that is, imagine you want to provide binding between your C++ libraries and some other, foreign language like the Python, JavaScript, or you name it, right? So now you get tools to do that. I will show you later how that's possible. In aggregate, modules provide an alternative that's far superior to hash includes and associated hackeries that you get. And so we have this new world, which is, you can, imagine our array of macros. And today we are with hash includes. The question that often asked is, how do we get there? What is there any transitional path from this messy world we are in today to the bright new future tomorrow? And the answer is yes. Though the spec for modules come with at least 2 ways of transitioning from the messy hash includes to the better structured modules, the global module fragments and header units. I would say, shortly a few things about those. So before I move on to the next issue, I wanted to just have you see clearly what is happening here. In conventional software development, you usually have this notion that you have a separation between interface and implementation. So the module keywords and image feature gives you this, this feature where you can say, this is, on the left-hand side here, you see clearly the interface of your components. And on the right side, you see the implementation of the functions that the period implementation are not particularly interesting to the consumer. So you have this clear separation. You put them into different files, and just like you used to do today, where you have header files and .cpp files, you can continue doing that today, tomorrow, or even today, I would say, where you have the interface definition in a separate file, and then you have the implementations elsewhere. But that is not required. So if you just want to have one single file where you put both the implementation and the interface, and then relying on this isolation, you can just do that. Right here, you have just one single source file that contains both the specification of the interface and the implementation of a function with its an array. So this is something to keep in mind if you work with what people call single header, header only libraries, where we just have one single file that contains everything. The additional feature that you get with modules is that they allow you to hide implementation details, which you can't do with header files. Okay, so where are we today? So like today, you have several efforts going on. You have, in terms of compilers, you have the 3 big compilers, MSVC, GCC, and Clang. So MSVC has an implementation which is production use ready, meaning that today I'm telling you, you can go and start using modules in MSVC for production. GCC was released last week, so just fresh hot, fresh out of the oven. It contains a preliminary implementation of modules. Or, in C++ 20 mode, you need an additional flag. But the implementation there is why it is labeled experimental. You can still try it in non-critical production use and see what's going on and give feedback to the GCC developers. They really love to have feedback in the users and bugs that people find. And then in Clang, there is a branch of Clang that contains, an active development of this feature that is already in C++ 20. Just like GCC, it is also experimental. You can check the source code out from Ian Sando's GitHub page and build and enjoy modules. I really encourage you to try modules in these 3 compilers to get a sense of it, to get prepared. I suspect by the end of this year and early next year, some of these experimental mode will turn into production-ready features. So that is the situation today in terms of compilers. MSVC gives you production-ready, implementation. GCC has modules in GCC 11, which was released last week, but it's labeled experimental. So once you have your compiler, the next thing you want is how do I build programs with this new fancy feature? Well, for build tools, you have MS Build, which has support for modules. And if you want to know how to use modules with MS Build, given the length of this talk, I encourage you to go and look at these 3 documentations. So a blog post by Will, which gives you an overview of C++ modules in Visual Studio, right? In the IDE, integration in the IDE and tool set. On the documentation page, the Microsoft documentation page, you have a walkthrough of how to build and use header units in MSVC, and also how you can import standard library headers in your code. So header units are some amalgamation of named module, real modules, and the header file. So essentially, they're header files that you import, meaning you try to use them as if they're modules. They're not really modules. They don't give you the isolation semantics that you get from named modules. You just get some of the performance benefit, which is where it is quite interesting. CMake has an experimental support for modules. It's really experimental. If you want to enable it, then you need actually to use a CMake macro that has experimental in the name. Builds 2 is another build system, build tool chain that has had that was among the first to have support for C++ modules. Boris Kalpachev has really nice tutorials and documentations about build 2 support. Build 2 is, it's being developed very actively, so things change quite fast. But everything that has released so far is pretty good. And very recently, the Maison build system has also added experimental support for modules. So here you have 4 build systems, 3 compilers, and you can use them in combination today. Like, you don't have to wait a year. They can try them today and experiment and build programs, get a sense of how to simplify your development, how to make you more productive. And the other thing that I want to mention is, of course, you have the compilers, have the build systems, and how do you use them? Last year, as I was mentioning earlier, I gave a talk at Vcpkg. You can watch video, more complete overview of how to program with modules. Daniela Enger just explained, some of the key technical aspects that I've worked hard to put behind the scene, but the key foundation, she called them the spices of what make modules very tasty. And of course, I mentioned Build 2 earlier. Boris Kolpakov last year also gave a talk at Vcpkg on practical C++ modules. And finally, I have this keynote on what it means to program with C++20. Like, this is really new language. It's really new language, and what you can expect from your compilers. Okay, so please go and try. You have the compilers, build tools, and then you have educational materials. And if you have any question, please give feedback. Now, the other aspect that I wanted to touch upon is that modules are actually a tooling opportunity. It is outstanding that C++ has succeeded in spite of what I would call the paucity of developer tools, semantics over developer tools. If you look at languages like, let's say, Python or Java or C#, they come with a rich ecosystem of developer tools, semantics-based developer tools, around them. And for C++, it has been really difficult. But thankfully, thanks to module, things are changing. So with modules, one thing that changed the game of compiling and using modules is that now you have a clear separation of interface from the implementation. You're telling the compiler, this is what everybody else needs in order to use this component. So what a compiler will do when it's compiling your interface is produce a complete semantics representation of your input source code, characters into a rich semantic data structure, which is the semantic representation. And every time you import module, it will reuse that representation. That is why using module is so fast. Like, you don't have to do the same work over and over. No, just once. The reuse of semantic representation, right? And on the other side, one of the problem is that this representation is compiler dependent. Today, SVC has its own representation, GCC has its own, which is very different from the representation that Clang has. One thing that I would like to see happen, going forward, is that all these major compilers somehow find ways to give access to that representation that they all produce. Right? If you have 3 compilers, they compile the same module, they will get 3 different representations. That's just insane, right? We just need one representation because we have only one program. So what they can be used for, this semantic rich data structure gives you access to the same content, but this time you no longer need a C++ compiler to understand it. You just need any dumb script or program that can traverse a graph. That's all you need, because the compiler has already done the work of turning your stream of characters into data structures that have semantics to them, right? And by getting access to that representation, what we're doing now is that we have the opportunity to give to the masses, to the, 5 million of C++ developers, access to the higher levels of C++ representation, right? If you want to interface your library with a, component written in a different language, most of the time people will use extern C. Those are the lower levels. Like, anything that's extern C says, basically forget about type checking, a bunch of other nice things that C++ gives you, right? That's just insane. We want to change that, and we have the opportunity to change that. So this rich representation can be used to generate a bunch of other, data for tools. We saw earlier talk on safety checking, runtime safety checking. Now you actually have a data structure that can aid that representation. If you want to do runtime JIT, you can use this representation to do that. You can defer code generation to program runtime so that you can collect more data, runtime data, use that to inform code generation, right? If you want to do types of distributed computation, you're doing computation, you want to farm, distribute, some part of computation to other machines, you can take your data structures, very rich, and then marshal them and then send them over network to the other machines. And you can do that because now you have a safe representation of the rich data structure that you're using. And by doing that, you just realize that you can actually expose APIs in C++ that use the higher levels of abstraction of C++ with other languages. You don't need to go to the, external C bug-ridden aspects of the language. So concretely, what does that mean? With the MSVC toolset, for example, the representation, we call it an IFC. When you have a module interface, you give it to the MSVC front end. You evoke cl.exe on that interface file. It's going to produce two things: the metadata, which is stored in an IFC file, has a suffix.ifc, and then the object code that gets linked to the rest, right? So this interface file is, the format is used to compile the module primary interface, partition interface, internal partition file, and also header units. These strange header file that turn into some kind of modules, right? And the binary format is quite simple. It is structured based on the principles of what I call the IPR, which is work that Bjarne Strustrup and myself did about 15 years ago, right? Time flies quite quickly. So with the IPR, you have a complete representation of what C++ is. It doesn't give you access to all the syntax ceremony. No, it gives you access to the rich semantics. Right, and that is what you need for most of these things. It is quite compact. The consistently in all the tests, and whether it is synthetic or production use, we found that the IFC files are at least an order of magnitude smaller than the PCHs that MSVC will produce conventionally through the conventional switches. So you get an order of magnitude saving there, and they are very easy to process. They are not memory dumped. They're on disk representation of rich data structures, and all you need to do is, how do I traverse a graph? That's basic things that we do all day, for everything that we do. So how does an IFC file look like? What does it look like? It's quite simple. It starts with 4 bytes. And then it has a header, and then header describes the names of the module it is for. We would say header units, and the architecture, and a bunch of other compiler flags, and so forth. And then it gives you some kind of forward reference to partitions. So partitions are just homogeneous tables used to represent each entity needed in a declaration, whether it is a type, a declaration, a context per function, and so forth. And of course, each of those entities have names. So you have a big string table that contains all the names that are in your source file, names and the strings and so forth. And near the end of the IFC file, you have what we call the table of content. The table of content is just an array of back references that tells you, here is the partition N, which its name, and how many entries there are, and what is the size in bytes of each entry in that partition. So quite simple. The structure of the IFC file, as I said, is very simple. It's just a bunch of homogeneous arrays. That's all it is. And you do graph traversal on that. If you want to know, because of the time limit, if you want to know more about IFC structure, there is an upcoming full description open to the C++ community. And along with that, I hope we'll also get tooling libraries. And I gave a more extensive explanation of the structures in my keynote last year, closing keynote at Meeting C++. So you can click on the link and watch it. And that was followed by a live Q&A. And you can also see what kind of questions that are asked here. If that's an answer, some of the questions have, please drop me an email. Don't hesitate to drop me an email. So what I want you to do today, given where we are, I want you to go and acquire those compilers, your favorite compilers from the three, like MSVC, Clang, and GCC. All three have some implementation of the C++ 20 feature modules. MSVC comes with it production ready. Clang has it, GCC has it in GCC 11, and Clang you have to acquire it from a branch, and hopefully that will migrate to the main development branch. And try any of these build systems that I hope you're using one of these for, right? And what I need from you is provide feedback to the C++ committee in terms of why we really need standard library modules. I know I've signed up for helping with that, but sometimes WG21 needs some kind of encouragement to do the right thing. Also, please provide feedback to your favorite C++ tools providers on making accessible the build artifact, these build module, interface files, so that you can build tools on top of them. They need this kind of feedback and encouragement. With that, I'm ready to take questions.
Great. Thank you so much, Gabby. That was really great. Modules are something that I'm really excited about, and it's always great to here's where we are and where we want to go. So we do have some questions in chat for you. Mm-hmm. One is, so I put up a poll in chat asking people whether they plan to use modules in production, mm-hmm. Or if it was a maybe, or if it was no. Most are yes, we plan to, or yes, we're doing. So some people said maybe, and one was that one big question mark for them is the state of the IDE and the whole pipeline support, IntelliSense, dump files, source indexing, things like that.
That's a good question. So Visual Studio, Visual C++ is the visual aspect of it. So now I think the previews that are available, I think 16.10 preview 2 or 3, and
2 is out now. 3 will be coming soon.
Okay, they have support for IntelliSense support for modules now. They started having it, and I would say every preview it gets even better and better. And I encourage everybody to try them out. It's really there.
Yeah, especially preview 3 will be coming soon, and preview 3 IntelliSense has come a long way in a lot of things.
Yes, I heard it has a lot of fixes, quality improvements. And please try them out. They are production ready. Please, don't hesitate.
Another question is the internal compiler data or IFC likely to play nicely with C++ reflection looking forward?
Oh, that's a great question. So I have been kind of, taking a step back because been very busy with the IFC. But my hope is that any C++ compiler that supports C++20 is going to have a representation of these things. So it is just natural that they will all jump on these representations to provide static reflection. For MSVC, I think the answer is yes. I don't write GCC code these days, but I would be very surprised if they went completely different ways and they don't reuse these data structures. With the IFCs, you don't, as long as you don't need to actually introspect the code in the same translation unit where you're asking the questions, you can use the IFCs to generate code that you compile at build time and link into your same program. So you can do some kind of build time reflection. It just won't be compile time in the sense that you ask the question for entities that are in the same translation unit. But if they're translation unit that are part of the same program, you can do that kind of build time reflection, which is already nice. And as an example, if you look at Qt, for example, it uses mock, and it needs some kind of meta, object protocol and that kind of stuff. So you can use the IFCs to replace a lot of the protocol stuff that, or at least provide a much better implementation of it. You don't need you wouldn't need Q object to macro to mark. You could just say, hey, give me that file and give me that type, or give me all the types that have these base class and so forth. And it worked with template nicely. So it is Mark on steroids.
Another question is about the Windows 10 SDK and providing modules, interface units to replace the old Windows headers.
Oh, okay. So that's more questionable for Windows, but I'll try to answer the best I can without stepping boundaries. So the Windows org has embarked on a new journey to provide different representation of Windows. What they call it now, they have a metadata description of Windows.h. And from what I know, I've seen that representation plays much nicer with modules than the old text-based Windows.h. Whether Windows.h itself will come as modules, I don't think that will happen. But what will happen is that from the API sets that they have on Windows, you're going to see coming online more and more components that are directly consumable as modules. But that's long-term planning. And first, they have to get the metadata representation of module Windows.h in first, which plays quite nicely with modules. And the next step is exposing the API sets as modules.
Yeah. Another question: if there is a common IAPR representation of a module, would it be reasonable to distribute that?
Yeah. So for me, the answer is unambiguously yes. I know there is a debate in the C++ community. Some people say, oh, they don't want to distribute. I think it is just a matter of time that as we start using modules more and more, we come to the realization that part of the benefit from module comes from reuse. Like if you want to do analysis like Sonny showed earlier, well, you have to save the IFCs and then you run your stuff on top of it, right? And then the next, if you want to use the result analysis, you have to save that, or you have to package it in a way that it can be reused by the next component that depends on your modules, right? So the distributing the representation of module interface is just a matter of time. It's a necessity. It will just take us as a community time to realize that this is actually a good thing to do.
Yeah. All right, we're pretty much at time now, but there is one last question which I think people would be interested in, which is people have talked a lot about potential speed up of modules for compilation. what kind of speeds up are we seeing? Is module compilation getting reasonably optimized yet in MSVC?
So we have not yet spent a lot of time optimizing modules in MSVC. We've just been busy trying to get the functionality there. But what we see from just like the naive implementation is that we have between 5 to 10x factor X improvements in build time, right? I saw an example, like I said, I saw an example yesterday having to do with device drivers and all of that. Someone is telling me that they saw 42, if I get the numbers correctly, 42x improvement. So no, I don't expect that number to be uniform for everybody, but it is impressive.
Yeah, totally. Okay, well, thank you so much. That's us at time now. So thank you for your time, Gabby, and for your
Thank
talk.
you very much,
and
Sai.
we'll see you next time.
Bye.
Okay, well, we're about at the end of our time now. So thank you for everyone for joining. A few things before we finish up. We do have a survey, which we would love you to fill in. I believe the link will be in chat in just a second. So please do fill out the survey. It helps us that, if we run this next year, we can make the event even better. If you'd like to ask more questions to the speakers, we've got a couple of potential options for you. One is right here at Learn TV tomorrow. There's going to be an Ask the Expert segment with folks who have been here. And then the day after, there's going to be a Teams event in the Reactor, which is going to be a bit longer, an hour long, so you can do some deep dive questions there. So all of those links will be in the announcement section. So if you go and look at that in Learn TV, it'll all be there. But thank you so much for joining. Thank you to all of our speakers who are all wonderful today, and to everyone who produced the content for our pre-conference sessions. I'd also love to absolutely specially thank all of the folks from the events and production teams who have helped to put this all together and make sure that we're running and we have all the Q&A and we have things, because last year when I ran everything from my laptop, it was nightmare. So thank you everyone for doing that and for helping out. And I will see you next time we run an event like this. Bye.